Well, let's do a couple examples. This is an example out of the Ball textbook. It's 7.9. What is the activity of water in a solution when the vapor pressure of water is 748.2 millimeter mercury at 100 C and at 1 atmosphere pressure? And assume the activity coefficient of water is 1. Everything's ideal. Oh, I guess I'm still black here. And ideal solutions. So we don't have to worry about activity coefficients or fugacity coefficients. All right, so let's see if we can see the activity of water. All right, picture's probably worth something here. So again, we're going to draw our box. And down here we have some water, which is a liquid. And up here we have water, which is in the gas phase. And note that I draw this as an enclosed box. I do that so that you'll have some sort of equilibrium going up and down here. If you just keep boiling the water and there's no constraint here, the water will all boil away like on the top of a stove. So I'm emphasizing here, and you have some sort of equilibrium established. All right, well, this is at 100 degrees C and is at 1 atmosphere. Now, what is the vapor pressure of pure water 100 degrees C? Well, 100 degrees C is the normal boiling point of water. Normal boiling point implies a boiling point when the atmospheric pressure is 1 atmosphere. So this implies that the vapor pressure of water at 100 degrees C is 1 atmosphere. So if you had pure water down here and you were at the boiling point at 100 degrees, the vapor pressure of water would be 1 atmosphere. It'd be boiling, in other words, at equilibrium. Now if we go back to the problem, at 100 degrees, 1 atmosphere, you don't have 100 degrees, you don't have the vapor pressure of water being 760 millimeters, 1 atmosphere. Instead, you have it 748. That means that the activity of water is less than 1. If it were 1, you'd have pure water, and it would be at 100 degrees, and it's boiling. At 1 atmosphere, you'd have pure water be boiling at 1 atmosphere. I hope I made that clear. All right, so we're assuming gamma is equal to 1 and so on. So the pressure of water in the solution is equal to the mole fraction of water in the solution times the vapor pressure of pure water in the solution. And we know at 100 degrees this is 1 atmosphere. That's the vapor pressure of pure water at 100 degrees. Boils under 1 atmosphere. We also know that the activity of water will be the activity coefficient of water times the mole fraction of water. And that's, we're saying the activity coefficient equal to 1, that'd just be the mole fraction of water. So the activity of water would be the vapor pressure. So the activity of water, or the mole fraction of water, is the vapor pressure of water divided by the vapor pressure pure water. So the vapor pressure of water in that solution over the vapor pressure of water pure. The vapor pressure given in the problem, 748.2 millimeter mercury. The vapor pressure of pure water at 100 degrees, that's when it's boiling, is 760 millimeter mercury. So that the activity of water in that solution is 0.9845. We'll put 4 significant figures, I guess. All right, so that's how you calculate activities, just as the ratio of the pressure divided by the above the solution divided by the pressure if the solution were pure water. All right, let's do this one. What's the mole fraction of ethanol in blood if the vapor pressure in breath is 0.07 millimeter mercury? Okay, let's go back and take a look there. What we have here is we have down here we have blood, and up here we have lungs. So the lungs, there's no I in lungs, we'll consider just as anything up here is in vapor and anything down here is in solution. And what we have is ethanol in the liquid phase is in equilibrium with ethanol in the gas phase. And let's assume there's phase equilibrium, so we have a dynamic equilibrium. Ethanol is going into the liquid, and ethanol in the liquid is going into the gas, back and forth. So the mole fraction of ethanol in the liquid phase, that's that X, is equal to the pressure of ethanol above the solution divided by the pressure of ethanol pure. All right, so what was the pressure? It is 0.07 millimeter mercury. The pure stuff is 115.5. So this is 0.07 millimeter mercury. The pure stuff is 115.5. So the mole fraction above the solution is 6 times 10 to the minus fourth. No mole fraction has no units. All right. For added interest here, this is how breathalyzers work. They assume that there's phase equilibrium between ethanol in your lungs, ethanol in your blood and ethanol in the lungs. So if they figure out what the concentration is here when you blow in a breathalyzer, then they can extrapolate and figure out what the concentration was in blood. When we just figured out what the concentration in blood was, it's 6 times 10 to the minus fourth. That's in units of mole fraction. So what is the, let's see if somebody blows this, whether the person is considered legally drunk and cannot drive a vehicle. Well, it's called the blood alcohol content. If it's greater than a certain amount, then you're considered drunk, and you can't operate a motorcycle or a car. For blood alcohol content, it has to be greater than 0.08 if you're over 21. It has to be 0.00 if you're under 21. In other words, there's no tolerance for drinking. If you're under 21 and you're drinking and you drive a car, no matter what your blood alcohol content is, you could be arrested for DUI. All right, but if you're over 21, you're allowed, somehow something magic happens at 21 and you're allowed to drink, but you can only drink up to a blood alcohol content of 0.08. What does this mean, 0.08? All right, 0.08 is 0.08% by volume. Okay, that's what that 0.08 means, 0.08% by volume. Now, this is mole fraction, so we'll have to do a unit conversion to see if somebody blows this in these units is actually legally drunk and should not be driving. Actually, you shouldn't be driving if you have a lower. 0.08 is pretty high. I don't know if you ever done that, but you probably don't want to operate a motor vehicle if you're 0.08. But anyway, so let's do a unit conversion. So remember, mole fraction is a mole, in this case mole of ethanol, divided by total moles, and let's assume the blood is all water. So this would be mole of ethanol plus mole of water. And let's assume that the ethanol concentration is small enough, so this would just be mole of water. So we look at this ratio. And let's convert that to volume percent. So we have, what do we say, 6 times 10 to the minus fourth mole of ethanol per mole of water. And let's multiply by the conversions here. We got 46 gram per mole. That's the molar mass of ethanol, so I've converted to gram. And then we're going to divide that by the density, 0.789 gram per milliliter. So that'll give us a volume of ethanol. And if we have a mole of water, we multiply by, convert it to grams, 18 gram per mole, and divide it by the density of water, which is 1 gram per milliliter. So there's a conversion. That'll give you the volume of ethanol divided by the volume of water. You put that into computer, or into a calculator, you get 0.002. And that is equal to 0.2%. So this is, if you blow this, do not drive. You're actually very drunk and probably near passing out. All right, well, anyway, that's sort of a digression. Thought you might be interested in that. Let's look at this. Here's another example. This is actually for introductory chemistry. You should know how to do this already, but nonetheless, we'll go ahead and do it. Well, we have this example in ball. Actually, problem in ball. What is the total vapor pressure above a solution that contains hexane and cyclohexane? Gives the amount of grams of those two compounds. The vapor pressures give the vapor pressures of the pure substances. Assume ideal behavior. Okay. Well, let's go ahead and do that. So the total vapor pressure, that's what we want, is equal to the mole fraction of hexane times the vapor pressure of pure hexane plus the mole fraction of cyclohexane times the vapor pressure of pure cyclohexane. The mole fraction of hexane, well, actually we can't do that quite yet. Let's do the number of moles of hexane. That will be the grams of hexane, 21.55 gram. The molar mass of hexane, 86.18 gram per mole. So this is 0.25 mole of hexane. Do the same thing for cyclohexane. The mass given in the problem was 64.14 gram. Divided by the molar mass of cyclohexane is 84.16 gram per mole. Number of moles of hexane, 0.762 of cyclohexane. So the mole fraction of hexane is the moles of hexane divided by the total moles, and that comes out to be about 0.25 to two significant figures. And similarly, the moles of cyclohexane, you do that or just subtract this, only two components, so 1 minus 0.25 is 0.75. So there's your mole fractions. The vapor pressure of the pure substances was given in the problem. So the total pressure is equal to, let's see what we're doing, the mole fraction of hexane, 0.25, times the vapor pressure of pure hexane, given the problem, 151.4 millimeter mercury, plus the mole fraction of cyclohexane, which is 0.75, times the vapor pressure of pure hexane, given the problem, 77.6 millimeter mercury. So the total pressure comes out to be 96 millimeter mercury. All right, so that should be familiar. Maybe you remember that from introductory chemistry. Now, what are the mole fractions of hexane and cyclohexane in the vapor? Oh, well, just let's see here. This is the total pressure, and we use the mole fractions in the solution. So what are the mole fractions in the vapor? Well, we go back. I'll just show you what we did here. Somewhere here we had way back in the lecture. Seems like so long ago. And it's coming up, and here it is. It's coming here. I guess we just, yeah. Oh, there it was, yes. Okay, so if we know the mole fractions, well, I guess we didn't do that, did we? Huh. Okay, so we know the mole fraction in the liquid, and we want to know what the mole fraction is in the vapor. So it'd be nice if we could solve this equation for y1 as a function of x1. I guess we didn't do that. Let's see if we can do that. Actually, no, we do have that. What am I talking about? There we go. y1 as a function of x1. All right, so let's go ahead and do that. Coming up, and here it is. So I'll just write that equation, sort of translate it. 1 will be hexane, and 2 will be cyclohexane. So the mole fraction of hexane in the vapor phase will be the mole fraction of hexane in the liquid phase times the vapor pressure of hexane pure divided by go away, the vapor pressure of pure hexane minus the vapor pressure of pure cyclohexane times the mole fraction of hexane plus the vapor pressure of pure cyclohexane. Put those numbers in. Let's see, mole fraction of hexane was 0.25. Vapor pressure, pure hexane, 115.5. I'll omit the units. Down here we have, sorry, it wasn't 115, it's 151. 151.4 over, and the difference in vapor pressure is 151.4 minus 77.6 times the mole fraction of hexane, 0.25, plus the vapor pressure of pure cyclohexane, 77.6. So this comes out to be 0.61. So note that the mole fraction of hexane in the liquid phase is 0.25, but the mole fraction of hexane in the vapor phase is 0.61. Is that what we expect? Well, yeah, hexane has a bigger vapor pressure, so you would think that would have a bigger contribution to the vapor phase than cyclohexane, which is less volatile. So that seems to check out. All right, so that ends this part of the lecture, and if you're still with us, we'll try for the next part of this lecture 11.